Everyone, and welcome to today's Physics Daily Booster. This is number 15 in our series. It is not listed on any of the advanced information. However, as we found out in our previous biology paper, we know that there are going to be questions on those other aspects because it's certainly not explicitly stated it's not going to be assessed. What we're going to do then is have a look at some of the basics of magnets. Hopefully our first little section here, we remember all the way down from kind of Key Stage 3 or even primary school, that if we've got two bar magnets and we place them together, if the poles are the same, so like poles, north, north, south, south, then they will repel. Whereas if they are opposite poles, north and south, they will attract. So if you remember nothing else about magnets, remember that first little box there. In terms of how we actually represent this magnetic field, what we have are these little lines on the diagram. Now, if we have a little look at the diagram in the bottom right corner here, bottom left corner, sorry, then what we find is this is a field line around a single bar magnet. So what we can see here then is these field lines represent magnetic flux, and the number of those field lines passing through a particular area is the magnetic flux density or magnetic field strength. So the more lines that pass through an area, the stronger that magnetic field will be. What we can see, they can ask us to draw the field lines around a bar magnet, in which case we're drawing the one on the left of the page here. So obviously we've got those lines that go from north to south, as we can see. And then we've got those ones that actually, they just kind of go off the page because those fields will be much larger that we can't quite see in that space. Do note the direction of the arrows. They always go from north to south. So what we usually find is on drawing the field lines, one mark is for actually drawing the lines themselves. Second mark is putting the arrowheads going from north to south. When you draw this, please make sure that you are not overlapping your field lines, because they will take marks off you for that. So field lines should not overlap. They should go from north to south with the arrows pointing in that direction. If we're looking at the bottom right of the picture here, we've got what happens when we have two bar magnets, one north, one south pole facing each other. So what we can see there are those field lines going between them. Again, those field lines will have the arrows pointing north to south. And then we obviously have the larger ones that go off. So what we find is when we're placing these two magnets together, they will always move in the direction that makes the field lines shorten. When we talk about magnets, there are two types of magnet we need to know about. The permanent magnet, this is one that's magnetic even when other magnets or a current is removed. And induced magnets are ones that are magnetic only when they're within a magnetic field. So basically they're made of a magnetic material that on its own is not magnetic, but when we place it inside another magnetic field, it will become magnetic. To try to explain how this takes place, we use something called the domain model. Now, when we're looking at a permanent magnet in terms of the domain model, what we're really saying is that the permanent magnet itself is made up of these small magnetic regions called domains, and they're all nicely lined up. Therefore, it is magnetic. If we consider a potentially magnetic material, iron, steel for example, they still have those domains, but they're not lined up. They're all kind of in different orientations. When we then place that iron into a magnetic field, it makes all those domains line up, and therefore it becomes magnetic. In some cases, when we remove that from the magnetic field, those domains remain lined up and it will remain magnetic. In others, take it out of the magnetic field, they return to their original positioning and therefore it's not magnetic. They can ask us about a compass and how it works. Now, hopefully we know a compass is all used to help us find our way when we don't really know where we are. Less likely to be using one these days with all the mobile phones that have all this stuff built into it, but in the olden times we had a compass. Now the compass itself has this little pointer that's floating inside on a little bit of fluid. The way that this works then is that compass is going to point towards the magnetic North Pole. Beware that the magnetic North Pole is not the same as just the North Pole on planet Earth. They are slightly different. Similar, but not exactly the same place. The reason that the compass is going to point towards the magnetic North Pole is because in the centre of the Earth, what we actually have is the equivalent of a large bar magnet. It's not actually a large bar magnet in the centre of the Earth, but what we have there with the molten iron core and the convection currents that it has basically generates a magnetic field around planet Earth itself. So that when we hold our compass in that magnetic field, it points towards the magnetic North Pole. Don't forget to join us again tomorrow for our next Physics Daily Booster, and if there are bits on the channel that we've done today that you're not 100% certain in, then do go have a little look at the main videos, use your revision guides, and as always I do recommend having a look at some past exam papers just to get a bit of a feel for the kind of questions that can come up. Because while this isn't explicitly listed as a topic, it's also not explicitly listed as something that won't come up. Therefore, is there going to be a mark on it? Probably. Will it be a large number of marks? Probably not. But remember, every mark is potentially the difference between one grade and another, so it's worth double checking if you're not 100% certain.